delta y by delta x is the average rate of change of y with respect to x, and dy by dx is the instantaneous rate of change. So again, notationally, for f prime of a, that is the value of the derivative evaluated at x equal to a, we write dy by dx at x equal to a. So we put either a straight line, vertical line here, or a bracket, but we are indicating here that we are evaluating that derivative at x equal to a. So d by dx means the derivative with respect to x of something. So d by dx doesn't stand on its own. We need to have, as I said, some function of x, some y, some f, something. We need to have something for the d by dx to operate on, some function. Also, we don't write dy by dx followed by f of x, because then you're doubling up there. It's either d by dx of y or d by dx of f of x. Right, let's have a look at what it means for a function to be differentiable at a, if f prime of a exists. It is differentiable, a function f is differentiable on an open interval, if it is differentiable at each point in the interval. So if we want to determine whether a function is differentiable on an open interval, we must determine that it's differentiable at each point in that particular interval. So let's explore the idea of differentiability with the next example. Where is the function f of x equal to mod x differentiable? You can do it algebraically or using the graph. Okay, first let's write the definition. F of x equal to mod x. It is equal to x if x is greater than or equal to 0, and minus x if x is less than 0. And I'll just sketch a quick graph here of that function. Y equals mod x. Okay, so we're going to do this. We're going to do this algebraically, and we're going to do it from first principles using the definition of the derivative of a function. Okay, so we've got a couple of options here. We've got for x greater than 0, for x less than 0, and then at x equal to 0. So we've got 3 cases that we need to investigate here. So let's start with the first one. If x is greater than 0, then mod x equals x. In the definition, we choose h small enough. Recall that in the definition, we are considering h to be very small and h going to 0 anyway, so that mod x plus h is greater than 0. Sorry, not mod x plus h is greater than 0. Then mod x plus h is just equal to x plus h. So if what's inside is positive, then mod x plus h is just equal to x plus h. So we can choose h small enough to ensure that x plus h is positive. Then for x greater than 0, we have f prime of x equal to, so using the definition, the limit as h tends to 0 of mod x plus h minus mod x all over h. Now x plus h is positive, so we can replace it just mod x plus h, we can replace just by x plus h. And x is positive, so we can replace mod x just by x all over h. Right, so the x's will cancel, and we'll get the limit as h tends to 0 of h over h, which is just the limit as h tends to 0 of 1. And we know the limit of a constant is the constant. So that's equal to 1. Oops. Right, so that is, so we found that by the definition of f prime of x, we've applied the definition according to the limit. The limit exists. So we can say, hence, f of x is differentiable for all x greater than 0. Okay, the second case is where x is less than 0. So similarly, for x less than 0, we can choose h small enough so that x plus h is now negative, i.e. mod x plus h is equal to minus x plus h because it's negative inside. Then for x less than 0, we have, again, we're going to find the derivative by using the definition as a limit. As a limit. So f prime of x is equal to, we've got the limit as h tends to 0 of mod x plus h minus mod x all over h. So now x plus h is negative. We replace it with minus x plus h minus, and x is negative. So we replace mod x with minus x all over h. You can see that the x's cancel. We get minus x minus minus x, so minus x plus x. So that gives us the x's cancel, and we get left with limit as h tends to 0. In the numerator, we'll get minus h over h. So that is the limit as h tends towards 0 of minus 1, which is just minus 1. So, according to the definition of the derivative, the limit exists for x less than 0. It's equal to minus 1. Hence, f of x is differentiable for x less than 0. So recall the definition for differentiability on the previous page. A function f is differentiable at a if f prime of a exists. It is differentiable on an open interval if it is differentiable at each point in the interval. So what we've shown so far is that f is differentiable for x greater than 0 and f is differentiable for x less than 0. Now we need to investigate the situation for x equal to 0. So this is the third case now. We need to investigate for x equal to 0. Right, let's write the definition of the derivative. let's write the derivative at x equal to 0 according to the definition. So we've got the limit as h tends to